everyone, this is Dr. GVR Seshagiri Rao, Associate Professor in the Department of Mechanical Engineering, Institute of Aeronautical Engineering, Hyderabad. In the previous session, we have discussed about the springs. So in the session, we have learned what are the basic terminology related to springs and what are the design considerations of springs and the types of springs we have studied. So in this topic, we will see problem solving of springs. So how to solve the problems according to given condition. So first we will see one problem on helical compression spring. So already you know the springs are many types, and in that the important type of spring is helical compression spring and then laminated spring. In design of helical compression spring, some parameters are important. So based on that design parameters, we will design a good helical compression spring. So here the given problem is design a helical compression spring for a maximum load of 1000 Newton for a deflection of 25 mm. So here the given type of compression of the spring, given type of spring is helical compression spring, and then the load is 1000 Newton. So it means the spring should withstand 1000 Newtons and a deflection for a deflection of 25 mm. So it is reflected under this maximum load 25 mm using the value of spring index as 5. So this spring index is very important when designing a helical compression spring. Already we have studied in the introduction part. So the maximum permissible shear stress for spring wire is 420 megapascal. The maximum permissible shear stress given for a spring wire is 420 megapascal. So it means it withstand the shear stress value is 420 megapascal. So the given type of stress is permissible stress. So not ultimate shear stress and not maximum shear stress. So here no need to take factor of safety value. And modulus of rigidity is 84 kilonewton per mm square. So the modulus of rigidity is 84. It is denoted by GRC. So we will see now problem and solution. Take Wahl's factor is K. So this relation, 4C minus 1 by 4C minus 4 plus 0.615 by C, where C is spring index. So the spring index is capital D by D. So it means it is a ratio of mean coil diameter to wire coil diameter. Clear? So the given problem is like this. Now we have to design a helical compression spring. So in design means we have to calculate all parameters by using empirical relations. Clear? We will see solution. So first of all, for any design problem, the first thing is you have to write the given data. What he has given in a problem and what he has asked, you have to identify. So then only we can apply the formulas. So the given data is here W, that is maximum load 1000 newtons, and then delta 25 mm. So the deflection is 25 mm, and C is spring index. So already I told you the spring index is mean coil diameter to wire diameter ratio. that is 5, and shear stress is 420 megapascal. So then this megapascal you can convert into Newton per mm square. So the 420 megapascal is equal to 420 Newton per mm square. So already you know. So here shear stress is equal to 420 megapascal. First convert into pascal. My mega into 10 to the power of 6 pascal. So pascal means 420 10 to the power of 6 Newton per meter square. So again convert into mm square. So 420 10 to the power of 6, that would be 10 to the power of 6 in Newton per mm square. So here get cancelled 10 to the power of 6 and 10 to the power of 6. So you will get 420 Newton per mm square. So that's why you can write, you can take directly the 420 megapascal into Newton per mm square is 420 mm square. So it means 1 megapascal into 1 Newton per mm square. Clear? So next is G, modulus of rigidity. G is 84 kilonewton per mm square. So convert into Newton per mm square. So here 84 into 10 to the power of 3. So so 84 multiplied 10 to the power of 9, and again convert into mm square, you will get 84 10 to the power of 3. So the mean coil diameter of the spring coil D not given, and let D mean coil diameter of the spring and the diameter of the spring wire, and small d. We know that the wall stress factor is 4C minus 1 by 4C minus 4 plus 0.615 upon C. Okay? So maximum shear, now apply the formula of maximum shear stress. So shear stress is equal to K into AWC by pi d square. So what is K here? K is wall stress factor. So that is 4C minus 1 by 4C minus 4 plus 0.615 upon C. So here 420 is shear stress available value, and K calculate, and AWC by pi d square. So you will get, so substitute the K value. K is equal to 4C minus 1 by 4C minus 4 plus 0.615 by 615 by C, where C is d by d. So mean diameter of the spring coil is, so D is equal to CD. So why? Because wire diameter already calculated in above step. So by using this relation, you may be calculated the diameter of the wire. If you know the diameter of the wire, you can calculate the mean coil diameter by using this spring index relation. So the mean coil diameter of the spring is, now substitute the above calculated value, C into D, this is 5D, and 5 times of the 6.41, so finally you will get 32.005, that is capital D. And the outer diameter of the spring coil is D naught is equal to D plus D, already mentioned here. So D plus D. So capital D already calculated and D also you know. So this is the outer diameter value. Clear? So next one is you have to find the number of turns of the coil. So it's the n number of active turns of the coil. This total number of coils you may be calculated based on the end conditions. So there are four types of end conditions. So already we have discussed in the theory part. So based on that given condition, you may calculate total number of turns. The active turns, the number of active turns are different. So how many coils, how many turns, how many turns of coils or turns are in active whenever applied load. So that is you can denote it with n. The total number of active, so that inactive coils also there. So the total number of coils you may be calculated by using the given condition. That is depends upon the condition. The condition is here squared and ground ends. If not given, not mentioned the end condition of the spring in your problem, you may assume any one type of ground end, one type of end shape. It may be ground or square. Clear? So, first number of, you know the number of active turns, you can calculate the total number of turns. So, that's why first use this equation, the delta. Delta is equal to AW CQ N by G into D. Okay? Or in terms of capital D or small d, AW dq by G small d to the power of 4 into N. So you can write this term d cube and d4, substitute C in terms of C. So that's why the equation you can write in terms of C, AW C cube into N by G D. Now, the delta, the deflection is 25, 8 into W into C cube into N by GD. So substitute the given load C and G value and a small d, Y diameter. So here you may be calculate N is equal to 25 upon 1.86. So the calculated value is 13.44, you can say 14. For squared and ground ends, here assumed the end conditions squared and ground end. The total number of turns are n dash is equal to n plus 2. So that's why n already we calculated 14, 14 plus 2. So this is the standard value for ground ends, n dash is equal to n plus 2. So the number of, you will get total number of turns 16. Next calculation is free length of spring. We know that the free length of the spring, so we have discussed in our terminology, the solid length and free length, two types of lengths are there. So in the free length, n dash d plus delta plus 0.15 delta. So free length means when it is compressed state. So n dash plus d plus delta plus 0.15 delta. So you may calculate the free length of the spring by using this relation. A total number of total number of turns multiplied with d plus delta deflection plus 0.15 delta. Pitch of the coil, we know that the pitch of the coil is free length upon n dash minus 1. N dash minus 1. So substitute those values, you will get pitch. So pitch means it is the axial distance between the adjacent coils. So what is the distance between one coil of spring, axial distance to the next coil? So you may calculate by using this relation, free length upon n dash minus 1. Clear? So like this, how to need to calculate all these parameters for designing a helical spring. Next we will see another problem of a helical compression spring is design a closed coiled helical compression spring for a service load ranging from 2250 newtons to 2750 newtons. So the axial deflection of the spring for the load range is 6 mm. So here given type of spring is closed coil helical spring, and the service load ranging from 2250 newtons to 2750 newtons. The axial deflection of the spring for the load range is 6 mm. Assume a spring index of 5. The permissible shear stress intensity is 420, here also given in this problem 420 megapascal, and the spring index also 5. And modulus of rigidity also same 84 kilonewton per mm square. So neglect the effect of stress concentration. So here don't consider effect of stress concentration. Draw a fully dimensioned sketch of the spring showing details of a finish of the hand coils. After the completion of design, with the calculated values, you need to draw a sketch of the spring. So now we will see solution, how to solve this type of problems. So first of all, given data, the given loads are here, two loads are there, minimum and maximum. The minimum load is W1 2250 newtons, and the maximum load is 2750 newtons. Delta is 6 mm. And C given D by D. So spring index, the spring index value is 5, and shear stress value 420 megapascal, 420 Newton per mm square. G is 84 kilonewton per mm square. So here convert into Newton per mm square. So the mean diameter of the spring coil, it assume D for a maximum load of W2, and then diameter of the spring wire, let us take D, small d. We know that the twisting moment on the spring is the load multiplied with the radius or distance. So that is, here load is, take maximum load, so W2 into D by D, mean coil diameter. But here mean coil diameter value is not available. Spring index is, so spring index is, you can write the capital D is 5 times of diameter of wire. So you can substitute in this twisting moment, and we will get the twisting moment in the terms of wire diameter. Clear? So now you can calculate the twisting moment. You know that twisting moment T is equal to 5 by 16 into tau into d cube. Here tau is shear stress, and then d is diameter of wire. So here the twisting moment already we calculated in previous step. The value here equate to this equation 6875D in terms of small d. So substitute those values. So you will get here diameter 9.13 mm. Once you calculated this wire diameter, so you may calculate the mean diameter of the spring coil. D is equal to capital D is equal to 5D. 5 times of the wire diameter. So we know that the outer diameter of the spring coil D naught is equal to D plus small d. So inner diameter capital D minus small d. So in this problem we don't know the outer diameter of the spring coil and then inner diameter. So that's why you can calculate the outer diameter and the inner diameter of the spring coil. So much you got 37.96 mm. The next step is need to calculate number of turns of the spring coil, number of active turns and number of total turns. So number of turns of the spring coil, let n, so that is number of active turns. It is given that the axial deflection for the load range from 2250 newtons to 2750 newtons. So that is for load 500 newtons is 6 mm. So here the range is 2250 to 2750. So what is the difference between these two? 2750 minus 250. So total 500 newtons difference. So what is the axial deflection for this range? For 500 newtons load, 6 mm. So that now write the formula of a deflection. W is equal to the delta is equal to 8W C cube into N upon G into D. So substitute the above values in this equation and find the number of active turns. After getting this number of active turns, you may calculate the total number of turns according to the given condition, given end condition. If not given in the problem, so you may assume any one type of end condition. So generally the coil helical springs are square and ground end. So here W is substituted 500. So don't take the maximum value in this deflection. So only need to substitute the range of load. So difference and C cube into n by 84 into 10 cube into small d. For squared and ground ends, the total number of turns, for squared and ground ends, the total number of turns n plus n dash is equal to n plus 2. So here calculated n is 10. So I have to add 2. So n plus 2, 12. So this is the final total number of turns. Next, free length of the spring. Since the compression produced under 500 newtons is 6 mm, therefore the maximum compression produced under the maximum load of 2750 newtons is, that is delta max. So only we have calculated for 500 newtons the deflection. So what is the maximum compression produced under the maximum load? So that is the maximum load is 2750 newtons. So delta max is equal to, so the given deflection is 6 deflection for load, that is 6 on 500 into 2750. So here you calculated for 500 newtons, what is the deflection? 6 mm. For maximum load, that is 2750 newtons, so what is the deflection under the maximum load? So 2750 multiplied with 6 divided by 500. So we will get 33 mm. So calculate the free length of the spring by using empirical relation. The empirical relation is n dash d plus delta max plus 0.15 delta max. So that is the delta maximum is this value 33 mm. So here you will get 152 mm. So pitch of the coil, we know that. So pitch of the coil is equal to free length. So that is LF by n dash minus 1. So n dash means here total number of turns. Don't substitute here, don't take n here. So this is not active turns. The total number of turns. So you will get 13.8 mm. So whenever the load value available in the range of minimum to maximum, then first need to calculate for range load and then again calculate the maximum deflection for particular maximum load. So then calculate the free length of the spring. So remaining formulas you can apply, and so whatever related dimensions are there related to helical compression spring, so by using these parameters you may calculate. So finally, after completion of all values, so draw a neat sketch of a coiled spring. See here drawn the diagram with the capital D, this is mean coil. mean coil dia, and small d, wire dia, and di already you know, inner diameter of spring, and it kept d naught, outer dia, clear, and then deflection 13.8 mm. So the total length, free length 152 mm. So like this, need to draw the neat sketch of a coil spring. So next model we will see a compression coil spring made of an alloy steel having the following specifications. Coil spring, and the specifications are mean coil diameter, wire coil diameter, number of active coils 20. Here in this problem, so no need to calculate the active coils. It's already given in our problem. The active coils are 20. So that is N. If this spring is subject to an axial load of 500 newtons, calculate the maximum shear stress, neglect the curvature effect. So here no need to consider the curvature effect. So if you are consider curvature effect, two types of shear stresses will be developed. One is direct shear stress, another one is curvature. Due to the curvature, shear stress, one more shear stress will be induced in the spring. So here neglect the curvature effect. Only one shear stress available, that is direct shear stress, to which the spring material is subjected. So here first given data, and then apply the formulas and calculate the maximum shear stress. Shear maximum. So given data, mean coil diameter and wire diameter, and given total number of active coils, and W is axial load. We know that the spring index where. So calculate spring index. Shear stress factor here 1 plus 1 by 2c is given. So this is empirical relation. So K is shear stress factor. So here we are not considering the curvature effect. So that's why here you should multiply with curvature, this shear stress factor. So you may assume the shear stress factor like this 1 plus 1 by 2c. The C is spring index. So neglect the effect of wire curvature. Okay. So here calculate directly shear stress is equal to Ks into 8W to d by pi dq. Clear? Now substitute the shear stress factor in W and capital D and a small d. So now we will get 534.7 Newton per mm square. So only thing in this problem, need to multiply shear stress factor. Why? Because here we are neglecting the wire curvature effect. Next problem, one more problem we will see. A helical spring is made wire of, fourth problem. So the wire diameter is 6 and as outside diameter 75, here only outside diameter is given. If the permissible shear stress is 350 megapascal, permissible shear stress 350, and the modulus of rigidity is 84. Find the axial load which the spring can carry and the deflection per active ton. So find the axial load W and which the spring can carry and the deflection per active ton. So that is delta per N. Delta not given and N also don't know. So given data, write down D naught is equal to 75 mm, shear stress is equal to 35, convert into Newton per mm square. G also convert into Newton per mm square. So calculate here mean coil diameter. Mean coil diameter of the spring is D naught minus D. So D naught already available, the outer diameter. So that 75 minus 6. 6 is here given the wide diameter. So you may get here mean diameter of the spring. So now you can calculate the spring index value. So D is already calculated and D small capital D is calculated and small d given in our problem. So spring index value 11.5. Now calculate delta per N and W axial load how much acting or how much load the spring can carry. So here also neglect the effect of curvature. So if you are neglecting curvature, effect of curvature, immediately multiply the shear stress factor. Shear stress factor. The shear stress factor is Ks is equal to 1 plus 1 by 2C. So what is C here? The C is spring index. Spring index. So that is C is equal to capital D by small d. So now substitute the above calculated value 11.5. So we will get shear stress factor 1.03. Now apply the maximum shear stress induced in the wire tau. Formula tau is equal to this value tau 350 Ks into AW d by dq. So in this, the unknown is W only. So now substitute the capital D and small d values in this relation. Tau is equal to Ks into AWD capital D by dq. So we will get the shear stress in terms of W. Shear stress already value you know, so substitute in this and then you may get the load value, axial load value. If you know the axial load, so immediately you can calculate deflection for active terms by using deflection formula. So AW dq by G divided by 4 into N. You can write in terms of C also this one. So delta is equal to AW dq by G dq into small d into N. So the d by d is C. So in terms of C, delta is equal to 8 into W C cube by GD to N. So like this also you can write. So deflection for active turn is calculated like this 9.96 mm. If you are considering this effect of curvature, you should multiply with the wall stress factor. So that is K. K is 4C minus 1 upon 4C minus 4 plus 0.615 on C. We are considering this effect of curvature. So substitute those values. So already you know the C value. So substitute in this equation. So you will get the wall stress factor. We also know that the maximum shear stress induced in the wire, the shear stress is equal to, in terms of wall stress factor, shear stress is equal to KAWC by pi d square. So W, so substitute the shear stress value in this equation and find out the W value. So here you will get the shear stress value in the form of in terms of W. So the shear stress, given shear stress 350 and calculate the W 384.4 newtons will get. So like this, how to solve this problem. And deflection of the spring, deflection for active turn. So deflection, you know this for empirical relation, AW to D cube into N by GT. To the power here W axial load, D is mean coil diameter, axial load, mean coil dia, and here number of turns, small d is wire dia. Deflection for active turn, so here you may write like this by using this formula, delta by N is equal to AW D cube by GT. So finally the deflection for active turn will get 9.26. So like this need to calculate the given problem. So these are the references I have taken. So Bandari, V Bandari and R.S. Kulmi and R.N. Norton. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.